We are going to solve a problem on deviations from ideal bond angles defined by the valence electron theory. But before we do that, let's review some of the basic concepts. So deviations from the bond angles are going to be caused by electrostatic repulsion, caused by electron groups on single bonds. The electron groups that could cause this repulsion would be a lone pair of electrons, such as that illustrated in this orbital representation of this V-shaped molecule, triple bonds, double bonds, and all of these electron groups have a stronger electrostatic interaction than a single bond in the order in which appear here. The strongest one would be the lone pair of electrons, followed by triple bonds, followed by double bonds. The V-shaped molecular structure that we have here, also known as the bend shape, have a molecular geometry of AX2E. E represents a lone pair of electrons. We can see that there are two bonds here, and that the angle that ideally should be 120 degrees between the two bonds is reduced, is less than 120 degrees because of the repulsion that these bonds experience caused by the lone pair of electrons. Another example of this is when we have a tetrahedral geometry of the electron configuration. Here we have another example in which the shape of the molecule is V-shaped or bent. The molecular geometry is an AX2, E2. It is E2 because it has two lone pair of electrons, as we can see in this diagram. And because these two pair of electrons are also causing repulsion of the bonds, the angle, the ideal angle of the tetrahedron is 109.5 degrees. It's going to be much less when we have this repulsion from the lone pair of electrons. Another example is seen here, in which we have a trigonal bipyramidal electron group configuration. The molecular shape that we have here is an AX4E, meaning that we have 4 bonded atoms and one single pair of electrons, and that this single pair of electrons is causing repulsion to the multiple bonds that we have here, multiple single bonds that we have here. So we have 4 bonds. The angles between those atoms bonded on the axial direction, following the cursor here, are going to be less than 90 degrees with respect to the other angles of the bonds on the equatorial position. And the angles that are on the equatorial position are going to be less than 120 degrees between the two atoms that are being indicated by the cursor, because again the repulsion of the single bond of electrons. The last example represents this octahedral configuration. The molecular shape is the square pyramidal, or AX5E. We have 5 bonds here, 5 bonded atoms, and the angles, the ideal angles for all of these between the different bonds should be 90 degrees. But because of the repulsion of the lone pair of electrons, these angles are going to be less than 90 degrees. So now that we have reviewed these concepts, let's go ahead and try to solve a problem that deals with the issue of non-ideal bond angles. The problem reads, assuming that we have different species, A, Fn, A meaning a central atom and F being fluorine atoms, N meaning the number of atoms, let's order of increasing bond angles these particular compounds, BF3, BF2, CF4, NH, NF3, and OF2. Please take a few minutes to think about the solution, work the solution, and then let's compare our answers. To solve this problem, the first step is going to be draw a Lewis structure for each of the different species. We are going to apply then the valence shell electron pair repulsion theory to define molecular type and the location of the lone pairs of electrons, which are going to be important to define the non-ideality of the ideal bond angles. Then we're going to identify single bonds that are perturbed by the lone pair of electrons. And finally, we are going to assign angles, ideal or modified, and rank the different structures according to their modified or ideal angles. So let's begin by drawing the electron structure or the Lewis structure for each of the species that are part of this problem. So for BF3, we will place boron as the central atom and the 3 fluorine atoms connected to boron. And then for this, if we do quickly the math for this particular compound, we know we have 24 electrons. 7 for each fluorine, 7 times 3 is 21, plus we have 3 for boron, so 24 electrons. If we place those electrons around the boron atom, around the fluorine atoms, we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's 18. And then we have 6 for the bonds that are made with boron. So that's a total of 24 electrons. Now we can see from this, for this species, that we have no lone pairs for boron. So this geometry is an AX3. And when we have an AX3 geometry, it's a trigonal planar shape. So that means that the angles that we're going to have between the bonds is going to be 120 degrees. Let's move on to BEF2. For BEF2, central atom will be beryllium. We have fluorine and fluorine as the atoms connected to the central atom. So a quick calculation will say that then we have 7 times 2 fluorine atoms plus 2 for beryllium. That's 16 electrons. Then we need to place 16 electrons. We'll start by placing those on the fluorine atoms first. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then we have, that's 12 electrons, and then we have 2 for each double bond, so that's 16 electrons. We cannot add any more electrons to beryllium. So then this type of geometry is going to be an AX2 because we have 2 bonds. The angle that we expect to have between bonds here is going to be 180 degrees. Let's move on to the third structure. The third structure would be that one of CF4. The central atom will be carbon, and we are going to have 4 fluorine atoms connected to that central atom. The number of electrons that we have here would be 7 times 4 plus 4 of carbon. That is 32 electrons. So we already know that we have 4 bonds, so that's 8 electrons. So we have to place the rest of the electrons, the 24 electrons surrounding the more electronegative atoms, which will be the fluorines. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 24 electrons. So if you look at the particular geometry for this molecule, we have an AX4, and the bond angles that we expect to have here would be 109.5 degrees. The next structure is NF3. We are going to place the nitrogen as the central atom and 3 fluorines connected to the nitrogen. The electrons that we have in this particular case will be 7 times 3 fluorine atoms plus 5 corresponding to nitrogen, we have 26 electrons. We have 3 bonds, so that's 6 electrons. We need to put 20 more electrons on the different atoms. We place 6 electrons on each fluorine, so that's 18. We need to place 2 more on the nitrogen. So this geometry, this molecular geometry is an AX3. And since we have a lone pair of electrons, E1. The angle between the different single bonds that we have here is going to be less than 109.5 degrees. In other words, we have a tetrahedral electron configuration, and this pyramidal shaped molecule will have less than 109.5 degrees because of the electron repulsion of the lone pair of electrons that we have here. Let's move on to the last structure, OF2. We are going to place as the central atom the oxygen, and we are going to connect 2 fluorine atoms to the oxygen. We are having 7 electrons per fluorine atoms times 2 plus 6 for oxygen. That's 20 electrons. We already have 2 bonds, so that's 4 electrons. We need to place 16 electrons. So that's 12. And we place 2 lone pairs on the oxygen. This electron configuration for the oxygen is going to be tetrahedral as well, and the molecular shape is AX2, AX1, E2. This particular angle is going to be much less than 109.5 because the bonds have additional electron repulsion from 2 pairs. This is a summary of the assignments of molecular shapes and the bond angles that we deduced from the previous analysis. Since part of this is assigning them in order of increasing bond angle, we can see that the smallest angle would be that for OF2. The explanation is because it has 2 lone pair of electrons that cause the maximum repulsion among this set. The next one will be that of NF3. The explanation for that is that it has 1 lone pair of electrons that causes deviation from the ideal angle of 109.5. The next one will be CF4, which has the ideal bond angle of 109.5. The next one will be that of BF3 with a bond angle of 120 degrees. And the last one would be BF2 that has the ideal angle of 180 degrees.